Hello, and welcome back to this course for psychologists and social scientists on causality. We're now in part 6 for machine learning, particularly for prediction. So for prediction, we're concerned with maximizing some performance metric. In fact, we mentioned this in the last session. We either want to maximize some metric for performance or we want to minimize some metric for error. So for instance, when you're fitting your linear models in R using LM function, you're probably going to be using the ordinary least squares solution, which means you're minimizing the least squares error, the least squared errors between your model and all the data that you're modeling. For instance, you might also be trying to minimize the negative log likelihood or maximize the log likelihood of your model, or rather the data under your model. And so that's really the goal of our predictive techniques. Now, the goal is also useful, as I mentioned, for parameter estimation as well, because when we're doing parameter estimation, we often need a model that fits the data well. And so just like we saw with ordinary least squares with linear regression, we used that predictive task to derive coefficients. And we also used that predictive task in a different way, where we generated two what I call interventional data sets. And for instance, I set the treatment equal to 1 for every single row, and I fed that to the model that was already fit. Using the predict function, I generated predictions. I did the same thing. I set treatment equal to 0, generated predictions, and then I contrasted the predictions under those two interventional situations. And so even though we had a predictive goal, which was minimizing the least squares, we were still using our model, in that case it was linear, to do parameter estimation. And if our model respects the causal structure, it has the right control variables in, all the backdoor paths are blocked and so on, then this predictive goal can also be very useful for causal applications. So we don't just get a coefficient out that sort of means, well, it's not really clear what it might mean, but we actually get a coefficient that does mean something in terms of the causal structure that you've assumed for your data. And so the reason is because estimating causal parameters is often the same as finding the model which does best at predictions, given some causal constraints. I.e., the main difference between predictive and causal models is that causal models will be constrained so they cannot leverage arbitrary correlations, but must work with what they are given. And as a result of that, they end up useful also for parameter estimation in the causal sense. Now, in contrast, it's quite tempting to just throw everything at a predictive model. And this is what's quite often done, because when we remove information to make a model causal, for example, we decrease its predictive performance. It's got less information that it can leverage. But at the same time, even though we might be reducing its performance, we may actually be increasing its robustness. Because if those variables that we've otherwise included are not really causally relevant for making those predictions, even though they might be spuriously relevant for a particular domain, often those are the variables that undergo some kind of covariate shift when we try to generalize our model to a new situation. So to that extent, I'm going to argue that even if we're just interested in prediction, we should still be considering causality, because doing so will help our models stay to generalize and also to be robust to certain covariate shifts. So apart from the utility of predictive models, we've seen in the previous session what these tasks might be, like automating coding, automating decision processes, and then also exploring the data for association. So when you're at the early stages of research, in fact, at any stage of research, and you want to just check that your theory contains variables that are also predictively relevant, you might want to throw some variables into the model, use your theory or your proto-theory to inform you as to which variables they are, and check that they are actually predictive of the outcome, because you would expect that, if they are causally relevant, then they're also useful for making predictions. And if you're really at the early stages, you could just put a whole load of variables in, whether or not you think that they are causally rated or not, just to see what comes out, just to give you an idea for which variables are important and which aren't. And we still have to be very careful about that, because as we've got here, if a machine learning algorithm can use a variable p to predict something, the assumption is that there must be some kind of causal relationship which links it to the outcome. But these causal relationships don't have to be directly from p to the outcome, so p to y, where it might be arbitrary to the extent that it might have some kind of indirect causal relationship to outcome. For example, here it's connected to y statistically via this fork structure. So we have x connecting y and p. And so it might look like p is very useful for predicting the outcome, but really it's only correlated to y because of the common cause x. So we do have to be very careful. And indeed, machine learning algorithms are just as sensitive to conditional independencies as linear models are. And I mentioned this earlier in the course. All of the rules of the directed acyclic graphs generalize beyond linear models. So when we're dealing with conditional independencies, we shouldn't just be thinking in terms of correlations and conditional correlations. So we really need to think more generally than that. This is not just for linear systems, but also for nonlinear systems. And to that extent, it's exactly the same for machine learning. When we use a machine learning algorithm to estimate the expectation of y given a set of predictors, that model will be just as sensitive to the underlying causal structure, which means that, for instance, if your structure or your data generating process is a fully mediated structure like this, you have x through m through y to y, and you include both x and m as predictors, the algorithm won't use x. So even though x is very predictive of y, if you don't include m, once you include m, you block the statistical flow of information from x to y. And if you look at the, say, some kind of machine learning explainability technique to help you understand which variables are most important, it will tell you that x is not important. So we have to be super careful, because if we don't know the structure is fully mediated like this, we might come to the conclusion that x is not actually related to the outcome at all. And I think if we don't think too hard about it, it might be tempting to come to the conclusion that because machine learning is so powerful, so flexible, so data-driven, that it's always going to find a way to leverage everything in the data. But it's simply not true. And actually, I have a paper here, which, if you're interested in this, you're obviously welcome to have a look at, called Trying to Outrun Causality with Machine Learning, Limitations of Model Explainability Techniques for Identifying Predictive Variables. And this paper is really all about, if our machine learning algorithms are highly sensitive, just as any other model would be, any linear model would be, to the underlying conditional independency structures in the data. And we can test this. We can use an example, and we're going to do this now, to see how much the machine learning model can tell us about the data. And the idea is that we're going to pretend we're at the early stages of research. We're confronted with some data, and we don't know what the theory is underlying those data. We're going to pretend we do know, for the sake of the example, the data are generated according to this graph here. And then we're going to see how far we can get using machine learning explainability techniques to uncover this underlying structure. And indeed, this was recommended, at least indirectly, by Yarkoni and Westphal in their paper, who said something along the lines of using machine learning to inform us about the underlying structure. But as we'll see, actually, it's very difficult to do this. Certainly very difficult to do it reliably. So let's start off by creating these data. So if you're not comfortable with simulating data yet, I do encourage you to pause the video, make sure that you can sort of read through this code here and check that indeed the code reflects the structure. I may have made a mistake, and you feel free to point that out. I've checked it through, so hopefully there aren't any mistakes. So I essentially generate all the random noise for each of these variables. All the independent variables without parents are generated first, like C1, C2, C3. We also have I and R1 and R2 here. C5 is generated here. 0.7 times C2 plus UC5, and so on and so on. So feel free to check that through. We generate the data according to this. Again, we pretend we don't know this structure, so that we can run exploratory machine learning techniques to check how close we can get to discovering it. So we're going to use Y as the outcome. And then, as is quite common in machine learning, we're just going to use everything that we have as predictors. And the hope is that if the variable is not important, it won't be used. If it is important, it will be used. And we're going to let the machine learning model do the work for us. We're going to use a simple train and test split for now. We're not going to look at cross-validation or train validation test, because actually we've got quite a large data set here. It's 1,000 data points. So there's enough to do a reasonable training, to have a reasonable training set and a reasonable test set. And also, we're not interested in doing model selection at this point. We're more interested in just fitting a reasonably strong model and seeing what comes out. So this is the code for doing that. So we import the library random forest. We're going to split the data into train and test. This is using exactly the same method that we've seen in the previous video, where we sample numbers from 1 to n, which is the maximum number of rows in the data. And then how many numbers do we want? Well, we want 60% for training. So we essentially pull 600 random numbers between 1 and 1,000 in this case. We use that to index our data. So we pull out the training split and the test split. We train our random forest on the training split. We have y as our outcome here, the little tilde indicating what predictors are, and we're just going to put a full stop there to indicate we'll use everything else in the data set, all the other variables. We're going to generate some test predictions here using the predict function and by passing in the test data. And we're going to generate some measure of that performance here. So here we can see this is the mean squared error. We have the true values of y in the test set. We take the difference between them and the predicted values of y in the test set, square them and take the mean. We're also going to get a baseline here. And this is a very important step actually when you're doing predictive models, is to make sure you have a reasonable baseline. If you have even multiple machine learning models that are all not performing particularly well, then you might want to check actually, well, what do I get with a very, very basic model, and just to check that we are doing better than a really dumb model. It's always good to have baselines that are equivalent to the models that other people have also run on the same research and the same data. But here I'm just using a simple mean baseline. That is to say, I take the average of the outcome and I compare it with the true values of the outcome. So it's not really a model. It's really just taking the mean of the outcome. I mean, it's still a model. It's just a super basic model, just as a baseline to check that we're doing better than just predicting the mean, for instance. So as I say here, it's important to have a baseline. Otherwise, it's difficult to say whether this is actually a good or bad performance. It might still be difficult to say whether it's good or bad. It depends on how useful that baseline is to you. But otherwise, you're just going to get an error, and it's hard to say whether that's low or high. What do you compare it against? And then here, we're going to use the function var imp plot, which is variable importance plot, which will give us a visualization of the importances of each of the variables being used in the random forest. And so this is one type of machine learning explainability technique. This provides us an estimate on average for how useful each of these variables are to the random forest. And indeed, like with variable importance measures, we have to be mindful that it's a kind of proxy for how strong the correlations are between the data and the outcome, but again, subject to the conditional independencies that exist in the data. So if we run these are the variable importance plots. We can see that the mean squared error on the test set is 0.17, and you compare that to the mean squared error of the baseline, which is 1.6. So indeed, we're doing a lot better than just predicting the average outcome here. So without going further into this, and arguably we should explore other models, make sure that we're not overfitting or underfitting the data too much. But just assuming that this is an adequate performance in terms of prediction, we're then going to see what it was using in the data to actually make that prediction. And so these are actually the variable importances, both in terms of reducing the mean squared error and including in terms of purity. And purity is a measure of predictive performance within a random forest or decision tree. So here we see that D is actually rated as the most important variable for reducing error. And indeed, it doesn't matter whether we're looking at node purity or mean squared error here, D is rated as the most important. In fact, these rankings are actually very similar. I think they're exactly the same ordering. There's just some slight differences in magnitude here. So let's just consider this plot on the left, given that we were looking at mean squared error anyway. So D is the most important variable. And if we look at the original structure, we see that D is a descendant of Y. And so it kind of makes sense that D is predictive of Y, because it kind of contains all the information that the other variables, the other ancestors of Y imparted on Y through the causal structure. So it kind of makes sense, but we might kind of mistake for whether or not D is a descendant or an ancestor of Y at this point. M here is given the next most important status, and that's reasonable as well. M is a mediator. There's a strong link between M and Y here. And then X is the third most over here. But, if this had been a fully mediated structure, as I argued earlier, X would be given very, very low importance. And then C4 is the next most important variable, which is this collider here, which is not really causally relevant to us, at least not in terms of our the main relationships between, say, X and Y here. But nonetheless, then R2 is given the next most level of performance, which has a link of 0.4 to the outcome here. I suppose that's reasonable, but actually these are really quite low in terms of their importances now. So all the others are really quite sort of, you could plot the sort of knee or the slope in this curve here and see when it sort of changes slope. So really, beyond C4, these are all quite sort of negligibly important for the prediction. And so we do have to be careful here, because it's arguable as to how much we can even take the top 4 results here and use them to meaningfully construct our graph. As I said before, it looks like X isn't that important, certainly not compared to M, even though actually X is maybe our treatment variable in a fundamental sense. Maybe we're deciding which variables we should try to intervene on. And fundamentally, maybe we have better access to X than we have to M. But this kind of suggests that X doesn't have much of a role to play in predicting Y. So it's really hard to use, in my view, it's really hard to use these techniques to sort of really infer something about the structure that's robust. And obviously now it's all very easy because we have the true structure, so we can see how it compares. But obviously in practice, you're not going to have that. So you've just got to take this table of results, and then I have to wish you good luck on the endeavor to try and piece together the structure using predictive approaches. But that said, it's a process of triangulation. I'm not expecting you to just use machine learning explainability techniques to derive the graph or completely determine your theory. This is an iterative process where you maybe use this information to inform your proto theory and update it, and maybe even manipulate or modify, your theory as well. So here we can try to identify important variables from a theoretical perspective, but as you can see, it is difficult. I wanted to give an example of a project I worked on fairly recently using a different explainability technique. So the previous example was using variable importance measures, which are sort of readily available as part of the random forest algorithm. They're easy to compute, but there's many other methods for explainability. And one such method is the Shapley method, which conceives of variables as players in a game. Essentially, those players are trying to maximize some outcome, in this case, the prediction of the outcome in your machine learning model. And the idea is to try and measure the contribution of each of those variables. And it's not so much that, okay, well, when I change this variable, the outcome changes by this amount, but it's rather in the context of all the other variables, how does each variable contribute? If you were able to disentangle each variable's contribution in the context of how they work together with the other variables. So it's really trying to account for interactions between variables and possible synergies between including more than one variable at the same time. So I like the method particularly because of its visualizations and how you can derive a lot of information using it. How reliable this is, I think that's still open for debate. There's a lot of papers talking about the limitations of all the different explainability techniques. But nonetheless, because this is part of exploratory research, we sort of take everything with a pinch of salt, and maybe we only look at the strongest results. And again, we use them to sort of guide, but certainly not determine the research direction beyond that point. So anyway, this research was looking at predicting dyadic desire, that is desire between romantic partners, how much desire they felt. And this bar plot here is really very equivalent to the plot we saw before for variable importances. It tells you how much each variable on average pushes the model in a certain direction. So in this case, it's just the magnitude. So actually it's not positive or negative, it's just the overall impact on the output. And so for instance, if dyadic desire is a scale from 0 to 10, then here we have sexual satisfaction impacting on average the prediction of dyadic desire by just over 2 points on the scale here. And actually, we can even plot this for individual data points. So here, each of these dots here is an individual in the data set, and we have the same number per row. So every row has all the data points on, and they're colored according to the value of the feature. So for instance, this red point out here is an individual with high sexual satisfaction. And in contrast, for instance, I don't know, just to take another example, here is a person that doesn't have sex regularly. So it's a low feature value for the feature or the variable have sex regularly. And so what we can see is, again, in this axis, rather than over here where we had absolute value on the model output, here we just have the value of the impact on the model output. So for instance, over here we have low values, an individual with a low value of sexual satisfaction, and that individual for that variable, for that value of that variable, has an impact of just over -10 on the prediction of dyadic desire. So for instance, here we can say, because there's a nice color gradient here from low values of sexual satisfaction to high values, we can say high values of sexual satisfaction tend to push the prediction of high dyadic desire. And conversely, low values of sexual satisfaction tend to reduce the prediction of dyadic desire. And the idea here is that if our model is doing a good job, we can draw conclusions about the sort of correlations that are in the data as well. Now, the trouble again is that because of the structure underlying this process, it's not really clear as to what the interaction is. And so even though it's nice to say, well, at least here we can say that people that don't want sex, that don't have sex regularly, have lower dyadic desire. That's very intuitive, but really what we're saying is that's what the model's doing. And the model's leveraging certain relationships in the data. We might be tempted to say those relationships also exist in the real world, but machine learning algorithms can be a little bit sort of fussy about what they do, a little bit particular, a little bit unique. And we might, for instance, use a different algorithm and have slightly different results. But this is something to check. You know, it's not like it's the same with all modeling processes. You want to make sure that those results are validated somehow. In this case, it was a very large data set, so we felt fairly comfortable in drawing conclusions about what might be true in the world based on what the algorithm was doing. The other benefit of Shapley is because it considers all of the interactions between variables, we can also look at interaction plots. So this is quite a nice three-dimensional graph where we have the impact on the prediction of dyadic desire, as we did along the x-axis in the previous slide. Now we have it on the y-axis. Along the x-axis, we have sexual satisfaction. And these are colored. These points are colored according to whether or not the individuals want more sex or not. So this is sort of like a binary categorization: people that want more sex, people that don't want more sex. And this is an interaction. You can see that depending on the group, depending on which group you're in, whether you want more sex or not, the relationship between sexual satisfaction and the level of dyadic desire changes. And actually, there's a sort of quite a nice crisscross pattern here that's quite clear and high in signal in the data. So this is quite almost a textbook example of an interaction plot in Shapley, and you can obviously draw some conclusions about this as well. And maybe this in some ways is more meaningful than drawing conclusions about the structure, because here you're saying, well, there's certainly some group effect here. There's some interaction between the groups of people as whether they want more sex or not and their outcome, and certainly an interaction with sexual satisfaction as well. So in terms of code, I've got Python code for this. I think there is a Shapley package in R, but this is super simple code. This is my random forest. I've actually stored it in this dictionary, which is called all last models, but that's basically just your random forest model. So you can dump your code in there from the previous examples where you've just got your random sklearn random forest that you've trained. Then we're going to use the shap.tree explainer to explain that model. So this chosen model is the random forest. We just pass that to this shap function. And we use that shap function to derive a set of Shapley values. And to do that, we have to pass in some data. And we pass the whole data set in. Once we've trained the model, we give it all of the data set. And it essentially looks at all of the values, looks at the behavior of the random forest, and it uses that to derive a set of Shap values, one for each variable for each data point in the data set. We can also run the Shapley interactions, which is how we get the sort of interaction information as well. Again, we pass in the same data here, and then I can simply plot using the shap.summary plot. And if you pass in show.false, then you have control over the figure sort of parameters. Otherwise, it will just display you a figure, and you won't be able to save it, for instance. It will do the plt.show, which sort of shows the figure, and then it sort of assumes you're done. But if you put show.false here, you can show it yourself, and then you get the opportunity to save the figure as well. You also have the option to either have a bar plot or the dot plot that we saw before. So this is the dot plot on the right, and this is the bar plot on the left. And so you can turn that on and off using the plot type equals bar or plot type equals dot, I believe. So it's super simple to get all of these results. Obviously, you have to be careful when we're interpreting them, but it's a very accessible process. So including all the variables makes the model sensitive to changes in variables which should have no causal impact on the outcome. I mentioned this already. We do have to be very careful, and the more causality that we can bring to the model, in my view, the more robust that model will be. On that note, it's quite well known that, at least it's well sort of publicized, that there are a lot of problems with artificial intelligence, machine learning, and discrimination. Here are just 4 headlines. Discriminating algorithms, 5 times AI showed prejudice. AI has a gender bias problem, just ask Siri. Millions of Black people affected by racial bias in healthcare. Photo algorithms ID white men fine, but Black women not so much. And one of the issues is that, we're leveraging any and all correlations. And even if we don't include gender in the data set, gender is represented in that data set in latent form. It's, there are certain, for instance, if you consider recommender systems that recommend products for you, and you've got a history of purchasing, you may not realize, but, your history of purchasing, even if that algorithm doesn't have access to your gender, may make inferences about your gender. And so that information is somehow contained within your purchasing history in a latent sense. It's not explicit, but it's there. And if this algorithm is leveraging those latent factors or even the explicit factors, if it does have access to those factors, that information, then you're going to get, biases in the way it's making predictions. And I think some might argue, well, those biases are useful to the algorithm because that's how it, for instance, makes good predictions for women versus predictions for men. But it can also be highly problematic because in many decision-making processes, we don't want it to be sensitive to gender or indeed any other socially or culturally protected factor. So we have to be super careful that our machine learning algorithm is not leveraging what it shouldn't. Now, if we're just using it for empirical research, then arguably we're just looking at what's in the data. We're not deploying these algorithms. We're not using them in practice in a way that could have major impact on people's lives. But I think that's a little bit to sort of displace the problem from ourselves. And I think as scientists, we still have a responsibility to consider these issues. Even if we're just doing research, we should be considering these issues. And just to sort of explain what I mean by this, in general, machine learning is very good at prediction, but it's not strongly informed by structure, at least not at the moment. There are a lot of researchers that are considering structure and causality. But just as an example, if there's that generative model that I showed you in the previous session called DALL-E, there's also a younger brother or younger sister of DALL-E called DALL-E Mini, which still has many parameters. It has 0.4 billion parameters, and it was trained on 15 million images. But if I asked it to generate a photograph of a cow in the Sahara Desert, I get this image. You can see that there's some grass bleeding over into this image. And this is because, most of the images of cows are in countryside regions. And conversely, if I ask it to generate an image of a camel in the Devon countryside, I get this. And you can see that the sand is sort of in the grass a little bit. It's not bad, but there's a little bit of bleed over there. And indeed, it's not able to reason independently about the compositional elements in these images. It's not able to say, well, I need to be able to independently generate the species or compared with the environment. And even though there's an association between these two things, it could be evolutionary, it could be geographical. In the data set, we see that there maybe is a correlation between cows and the environment they're seen in. Actually, for the sake of an image and what I am imagining in my head, I should be able to independently compose these objects. So I shouldn't get bleed from the environment when I independently specify the Sahara Desert to the animal. And so as a consequence of the fact that we're not considering structure enough in machine learning, we get bias, poor robustness. This is biased because you can see the correlations associated with cows, and the countryside is bleeding into the generation of the image. And we have a reliance on diverse labeled data. We could argue that, all we need to do, is take a whole lot of cows to the desert, take lots of pictures of them, and then introduce those pictures into our data set. And then once we've done that, we're going to rebalance the sort of correlations, and we're going to make these two independent. But that's super expensive. So, getting hold of diverse labeled data that can allow you to get unbiased predictions or of anything or generations of anything is very expensive. Now, to be fair, DALL-E 2, the one that I did show you before, when I asked it to generate the same images, it actually did a much, much better job of generating those images. So these are still fake images using the same prompts as we saw on the previous slide. But now DALL-E 2 had 3.5 billion parameters and was trained on 400 million images. So the scale of this is absolutely huge. Maybe the results tell us that, all we need is more data. Again, that's not always possible. Furthermore, when I asked the model to create an image of a cow on the moon, it couldn't do it. I tried various prompts. I tried photograph of a cow walking on a lunar landscape. And again, it wasn't able to do it. So instead, it gave me an image of a cow in front of the moon. Perhaps because it's never seen any image of a cow on the moon, it was unable to compose me an image that resembled that prompt. And so it seemed that even in the limit of this huge data set, these hugely parameterized models, it was only able to sort of interpolate between examples that it's already seen. And this again shows how important it is to consider structure with your machine learning. We could have maybe made the job of this algorithm easier if we had given it some kind of inductive bias, some kind of structural knowledge. Now, for DALL-E 2, that may not be possible because it's such a diverse model. It's intended for so many different purposes. There wouldn't be one sort of structure that would represent all those user cases. But really, there's a lesson here for simpler machine learning algorithms, for your random forests, on your tabular data sets, that some structure is very important. And we already have the tools, now you follow this course, to do that, to starting considering the causal structure behind your data generating process. And we can use that to create better predictive models. Because at the end of the day, even if all we need is another 10 million data points, many applications we can't scale in that way. We can't just collect another 10 million data points for cancer patients undergoing chemotherapy to understand the efficacy of treatment. We just can't do that. So it's very important, in my view, to consider the structure underlying the problem, even if you're just designing a predictive model. So undertake machine learning for prediction with caution. And the main lesson here is that we cannot escape causality. So even though maybe it feels like we had causality in the first half of the course and now we're going on to machine learning and we're sort of forgetting all about it, that's absolutely not the case. I really want causality to be a common thread throughout the whole course. Okay, well, that's the end of the session for the day. And I look forward to seeing you in the next one.